This is an introduction to the core theory. The core theory is a quantum field theory encapsulating knowns concerning quantum field dynamics. We have first the electron, the muon, the tau, and they have electric charge of -1. The electron neutrino, the muon neutrino, the tau neutrino, which is neutral. Then the up quark, charm quark, top quark, which have a charge of positive 2/3. Then down quark, strange quark, and bottom quark, which have a charge of -1/3. We have gravitation, which includes gravity, space-time curvature. The photon, which includes electromagnetism. 8 gluons in regard to the strong nuclear force, W and Z bosons, weak nuclear force, and then the Higgs bosons. There are 2 types of quantum fields, fermions and bosons. The core theory, in essence, are the laws of physics underlying all of life expressed in a single equation. The equation is the quantum amplitude for undergoing a transition from one specified field configuration to another, expressed as the sum over all the paths that could, in theory, possibly connect them. Here I go into an explanation of the core theory. The core theory incorporates quantum mechanics, space-time, gravity, other forces, matter, and the Higgs boson. The world of our everyday experience is based on the core theory, a quantum field theory describing the dynamics and interactions of a certain set of matter particles called fermions and force particles called bosons, including both the standard model of particle physics and Albert Einstein's general theory of relativity in the weak gravity regime. The capstone is a single formula, the Feynman path integral for the core theory. Pertinent to know is that there are 2 kinds of quantum fields, fermions, which, as I have said before, are the matter particles, and bosons, the force particles. Fermions are the particles of matter. They take up space and explain the solidarity of the ground on which can be walked, and the chairs in which we sit. Bosons are the force-carrying particles. They give rise to macroscopic force fields, such as those of gravity and electromagnetism. In quantum field theory, information specifies the properties of a particular field, or equivalently, the particle with which it is associated. Each particle has a mass and a spin. Elementary particles, or vibrations of quantum fields, do not have a size. Their spin is an intrinsic property, not the revolution of their bodies around an axis. Every particle associated with a particular field has the same spin, i.e. electrons equal spin -0.5, gravitation's spin -2. How particles interact is governed by their charges, or their electric charge, but the other forces, such as gravity and nuclear, also have charges that are associated with them as well. The charge of a particle tells how it interacts with the field that carries the associated force. Electrons' electrical charge, -1, interact directly with photons, which carry the electromagnetic force. Neutrinos with the electric charge 0 do not interact directly with photons at all. They can interact indirectly, however, since neutrinos interact with electrons, which then in turn interact with photons. Photons are neutral. They do not interact directly with one another. The gravitational charge is the energy of the particle, which is equal to the mass times the speed of causality, or the speed of light, squared when the particle is at rest. Every single particle has a gravitational charge. Albert Einstein taught that gravity is universal. All of the fermions that are presently known have what is called a weak nuclear charge, so they interact with W and Z bosons. Half of the fermions that are known to exist in the universe have an interaction with the gluons that carry the strong force. These fermions are called quarks. The other half do not. These are called leptons. Up-type quarks have a charge of positive 2/3, and down-type quarks have a charge of negative 1/3. The strong force is so strong, in fact, that both quarks and gluons are confined inside particles, like protons and neutrons. They are never visualized directly. The charged leptons are the electron and its heavier counterparts, the muon, represented by the Greek letter mu, and the tau, represented by the Greek letter tau. And there are 3 neutrinos associated with them: the electron neutrino, the muon neutrino, and the tau neutrino. And then there is the Higgs field and its associated particle, the Higgs boson. Proposed in the 1960s, the Higgs boson was discovered at the Large Hadron Collider in Geneva, Switzerland, in the year 2012. But what makes the Higgs special is that its field has a non-zero value, even in empty space. All of the particles of which everything is made are constantly in a Higgs field, and that affects their properties. Most pertinent, it gives mass to the quarks and charged leptons, as well as to the W and Z bosons. Included in the analysis of how quantum mechanics works is the Schrödinger equation for the core theory, which satisfactorily explains how the wave function of a given quantum system evolves or changes from one moment in time to the next. One way of encapsulating this information is the path integral formulation of quantum mechanics, first pioneered by Richard Feynman. The wave function describes a superposition of every possible configuration within an earlier wave function. Feynman's equation, like Schrödinger's, is reversible in the Laplacian sense, but when things start to be observed, quantum mechanics violates reversibility. The quantity W is the amplitude to move from one field configuration to another. It is given by a Feynman path integral over all of the specific ways the fields could evolve in between. An integral is a simple way of summing an infinite number of infinitely small things, such as when one adds up infinitesimal regions in order to calculate the area under a curve. What is it that we are integrating or summing up? For each and every path integral that a system can take, there is a number to calculate called the action, traditionally represented as S. If the system is jumping all over the place, its action will be very large. If it moves more smoothly, the action will be relatively small in comparison. Everything depends upon a point of reference. The concept of action along a path plays an important role even in classical physics in regard to classical mechanics. Among all of the possible paths that we humans can imagine the system taking, the one it actually, not potentially, does take, the one that obeys the classical equations of motion, will be the one that has the least action. And so every classical theory can be defined by what the action for the system is, and then looking for motions that minimize it. But Richard Feynman put forward an approach in which one can think of a quantum system as taking every path. To each path is an associated phase factor. And this notion, or notation rather, tells one to take a constant, in this case Euler's number, E equals 2.7181, and raise it to the power of I, the number given by the square root of -1 times the action S for the path. The phase factor is a complex number. Summing up all the contributions for all the paths will generally involve many positive and negative numbers, and everything will cancel out, or nearly so, leaving a small answer. The world and everything known to exist in it is well modeled by classical mechanics. It is classical behavior that gives the largest contributions to the probability of quantum transitions. Now the equation presented will be taken apart into its smaller components for further clarification. The quantum mechanics portion of the equation shows that the amplitude is being written as an integral over a collection of fields followed by Well, we'll skip that part. But the fields that are included are indicated in the notation D, G, D, A, D, Phi, and D, key. The letter D translates as to the infinitesimal quantities that add up in the integral. The other symbols stand for the fields themselves. The gravitational field is represented as G. The other bosonic force fields, electromagnetism, strong and weak nuclear forces, are grouped under the term A, or alpha. So all of the fermions are collectively labeled Psi, or the Greek letter. And then the Higgs boson is the Greek letter Phi. The notation expresses e to the power I is the square root of -1, and everything following I is the action S for the core theory. What it says is to integrate over all the paths that all of the fields can take a quantity given by raising e to the power of I times the action. Many professional particle physicists spend their entire lives writing down different possible actions for different collections of fields. Every physicist starts with this one for the core theory. The action is an integral over all of space, over all of time, period, in between the initial configuration and the final configuration. But that's what the notation is doing. X, for example, stands for the coordinates on all the possible dimensions of space-time. And the 4, the raised to the power 4, is reminding one of the fact that space-time is 4-dimensional. There is an extra factor under space-time, which is the square root of -g, negative gravity. This has something to do with gravity, obviously, and in particular the fact that space-time is curved. And this accounts for the fact that the volume of space-time, which is being integrated, is affected by how space-time is curved. All of the terms inside of the square brackets in the equation are the different contribution to the action from all the various fields, their intrinsic properties, and how they are interacting with one another. They are in the categories of gravity, other forces, matter, and Higgs. The gravity term reflects the pristine elegance of the symbol A, or alpha, in the Greek alphabet. Einstein's theory of general relativity, which he had his theory of special relativity before he came out with his theory of general relativity, the quantum or quantity R is called the curvature scalar and characterizes how much of a certain kind of space-time curvature is present at any given point. It is then multiplied by a constant, m, with the superscript 2 subscript p over 2, or e with the subscript p is the Planck mass. This is simply a way of expressing Newton's gravitational constant by the letter G, which characterizes the strength of gravity. Both the speed of light and Planck's constant of quantum mechanics are set equal to unity. The curvature scalar, represented by the letter R, can be calculated from the gravitational field, and the action for general relativity is proportional to the integral of R over a specified region of space-time. But in order to minimize this integral, it leads to Einstein's field equation for gravity. The term labeled other forces includes 2 appearances of a quantity F and a few superscripts and subscripts. F is called the field strength tensor, and it includes contributions from electromagnetism and the strong and weak nuclear forces. In essence, the field strength tensor identifies how much the field is twisting and vibrating through space-time. The curvature scalar informs how much the geometry of space-time itself is also doing the same. For electromagnetism, the field strength tensor incorporates both the electric and the magnetic field. Superscripts and subscripts label different sub-quantities, such as when field photon, gluon, W, or Z boson is being inquired or focused upon. two quantities, like the two F's in this term, mean the sum over all the possibilities. This is a compact notation, allowing to hide great complexity in a few symbols. This one term encompasses the contributions from all the different force fields. Things start to become complicated in this part, however, of the equation, labeled matter. The matter fields are the fermions, represented collectively by the letter phi, which is a Greek letter, obviously. As with the bosons, this one symbol includes all of the fermions. The Greek letter gamma stands for the Dirac matrices, introduced by physicist Paul Dirac, an essential role in how fermions behave, including the fact that fermions have both antiparticles as well as particles. The D stands for rate of change in regard to the field, indicating how much the fields are evolving or changing through space and time. A coupling or interaction between the fermions and the force bosons depends on how the fermions are charged. For example, the way that an electron interacts with a photon is characterized by this term in the action. The term next to it involves a different kind of coupling between the fermions and the Higgs field. This term encapsulates how fermions and the Higgs field interact with each other. And then we have a symbol that indicates the mixing matrix. It is a fact that fermions can mix with each other. For example, a top quark decays into a particular mixture of down, strange, and bottom quarks. One fermion field has a subscript L and the other a subscript R. And these letters stand in for left-handed and right-handed fields. The phenomenon of parity violation was a shocking discovery to many particle physicists. The term HC stands for Hermitian conjugate. In other words, in order to describe this, it is indicating that the first term is a complex number, but the action needs to be a real number, a purely real quantity. The last part of the equation concerns the part of the action that is devoted to the Higgs field. The kinetic term represents to what measure the field is changing, and the second term, the potential, or potentia, represents how much energy is locked up in the field even at times when it is not evolving or changing at all. The second term is pertinent and special. Like all other fields, it wants to have the lowest amount of energy, unlike the other known fields. In its minimum energy state, the Higgs field does not vanish but has a non-zero value. Therefore, its potential or potentia energy is higher when the field is zero than it is when the field is non-zero. The Higgs field has a presence even in empty space, and it allows it to affect the other particles that move through it. The core theory, or simply one equation that informs concerning the quantum amplitude for the complete set of fields from an initial starting configuration, part of a superposition inside a wave function, to a final configuration. And then there is dark matter in the universe, and unfortunately it does not fit well concerning any of the known fields. And almost every physicist in the history of mathematics at the present century, that of the 21st century, thinks that there are more particles and fields to be found in the universe. Not to mention other universes, bubble universes from string theory, for example, that might exist. And these other fields and particles might exist at higher masses and energies, but they either interact very weakly, like dark matter, for example, or they decay away very quickly. For example, neutrinos have a mass, but it has not yet been experimentally verified that the terms in the equation are the ones that are responsible for the masses of the neutrinos themselves. Interestingly, the core theory does not provide a complete theory of the fields that are known to be there. For example, we might want to look at Stephen Hawking's work on this. This is a problem for things such as quantum gravity. As far as physicists are concerned, the equation works if the gravitational field is very weak. However, it does not work when gravity becomes strong. For example, near the event of a Big Bang or inside that of a black hole. I also recommend Roger Penrose for this. And the first integral sign in the equation, which indicates the summation over all the different field configurations through time, there is a subscript, kappa less than alpha. Kappa is the wave number of a particle mode of a field. Alpha is the ultraviolet cutoff. I recommend Ken Wilson on this part to think about every field as a combination of modes, each constituting a vibration with a specific wavelength. The wave number labels these modes. Larger kappa corresponds to the smaller wavelength and therefore higher energies. This notation indicates low energy, weak field situations, but still also includes all of the particles and fields that describe the universe, our planet, and all of the things that exist within it. And so, in conclusio, the core theory can be described as that which indicates the gravitational pull of the sun on the Earth, but not what was happening at the Big Bang, for example. And so there are many models that have been theorized. Inflationary theory is just one of them. See also gravitational potential energy. This material is given usually to graduate level physics courses. I wrote it down in order to preserve it for the next few centuries and beyond. The existence of our species on this planet and what science and humanities faculty of reason has been able to produce from its finest and brightest of minds. The theory is extremely precise and well-defined, considering its limits are built only into the formalization or formalism of it, leaving zero ambiguity. And as science in its history continues to learn more about the universe, the historian will add to his history. Perhaps a more comprehensive theory underlying the present one will be found. Core theory, however, is an articulated, accurate, cogent description of natural phenomenon in nature. And its claimed domain and the fact of such theory being assembled and composed is one of the greatest triumphs of human intellectual history.